Physics is a branch of natural science that focuses on the study of matter, including its fundamental components, motion and behavior in both space and time, as well as the associated concepts of energy and force. Understanding how the cosmos acts is the core objective of one of science's most fundamental fields, physics. A physicist is a scientist who focuses on the discipline of physics. Due to the involvement of astronomy, physics is not only one of the oldest academic fields, but also quite possibly the oldest. Physics, chemistry, biology, and some disciplines of mathematics have been a part of natural philosophy for a large portion of the previous 2 millennia. But during the scientific revolution in the 17th century, these natural sciences became independent research fields. The limits of physics are not clearly defined, and it interacts with many interdisciplinary fields of study, including quantum chemistry and biophysics. The underlying mechanisms investigated by other sciences are frequently explained by new concepts in physics. And this opens up new directions for investigation in these and other academic fields like mathematics and philosophy. New technologies are frequently made possible by improvements in physics. For instance, improvements in our understanding of electromagnetism, solid-state physics, and nuclear physics directly influenced the creation of new goods that profoundly altered modern society, such as television, computers, home appliances, and nuclear weapons. Improvements in thermodynamics sparked the industrialization of society. And improvements in mechanics provided the impetus for the invention of calculus. Core theories. Even though physics works with a wide range of systems, all physicists use the same theories. Each of these hypotheses has undergone extensive experimental testing and been found to be a reliable approximation of nature. For instance, if an object is far larger than an atom and moving at a speed much slower than the speed of light, the theory of classical mechanics can adequately describe the object's motion. These theories are still being actively researched today. 3 centuries after Newton's original formulation of classical mechanics, the extraordinary element of that theory known as chaos theory was found, 1642 to 1727. Any physicist, regardless of their area of specialization, is required to be knowledgeable about these fundamental ideas because they are crucial resources for study into more specific issues. These include electromagnetism, special relativity, thermodynamics, quantum mechanics, and statistical and classical mechanics. Classical mechanics, acoustics, optics, thermodynamics, and electromagnetic are all established branches and areas of physics that were understood and well developed before the turn of the 20th century. The study of forces acting on bodies or bodies not subject to acceleration is known as statics. The study of motion without considering its causes is known as kinematics. The study of motion and the forces that affect it is known as dynamics. Classical mechanics can also be divided into solid mechanics and fluid mechanics, collectively known as continuum mechanics, the latter of which includes such branches as hydrostatics, hydrodynamics, and hysteretics. The study of sound production, regulation, transmission, and reception is known as acoustics. Ultrasonics, the study of sound waves at extremely high frequencies that are outside the range of human hearing, bioacoustics, the physics of animal cries and hearing, and electroacoustics, the electronic manipulation of detectable sound waves, are all significant contemporary fields of acoustics. In addition to visible light, infrared and ultraviolet radiation are also included in the field of optics, which is the study of light. These 2 types of radiation exhibit all the same optical properties as visible light, with the exception of visibility, such as reflection, refraction, interference, diffraction, dispersion, and polarization of light. The internal energy held by the particles that make up a substance is known as heat. Thermodynamics studies the interactions between heat and other types of energy. Since their close relationship was established in the early 19th century, electricity and magnetism have been studied as a single discipline of physics. An electric current creates a magnetic field, and a changing magnetic field causes an electric current. Electric charges at rest are the focus of electrostatics, moving charges are the focus of electrodynamics, and magnetic poles at rest are the focus of magnetostatics. Modern. While most of modern physics is concerned with the behavior of matter and energy under extreme circumstances or on a very large or very tiny scale, classical physics is often concerned with matter and energy on the regular scale of observation. For instance, the smallest size at which chemical elements can be distinguished is used to explore matter in atomic and nuclear physics. Since it deals with the most fundamental building blocks of matter, elementary particle physics operates on an even smaller scale. This field of physics is also referred to as high-energy physics due to the extremely high energies required to produce a wide variety of particles in particle accelerators. Ordinary, sensible concepts of space, time, matter, and energy are no longer applicable at this scale. In contrast to classical physics, the two main theories of modern physics offer a different interpretation of the ideas of space, time, and matter. While quantum theory is concerned with the discrete nature of many occurrences at the atomic and subatomic level as well as the complementary aspects of particles and waves in the description of such phenomena, classical mechanics approximates nature as continuous. The special theory of relativity deals with motion in the absence of gravitational fields, while the general theory of relativity deals with motion and its relationship to gravitation. The theory of relativity seeks to describe phenomena that occur in a frame of reference that is moving with respect to an observer. In many fields of contemporary physics, the theories of relativity and quantum mechanics are both applied. Difference. Although physics seeks to identify universal laws, its theories have clear areas of application. In general, systems with substantial length scales bigger than the atomic scale and movements that are far slower than the speed of light are described accurately by the rules of classical physics. Observations outside of this area do not line up with those made by classical mechanics. The framework of special relativity, developed by Einstein, allowed for a correct description of systems whose constituent parts have speeds close to the speed of light by doing away with concepts of absolute time and space in favor of space-time. Quantum mechanics, a probabilistic understanding of particles and interactions that enabled an accurate description of atomic and subatomic scales, was developed by Planck, Schrödinger, and others. Later, quantum field theory combines special relativity and quantum mechanics. With the help of a dynamical, curved space-time made possible by general relativity, enormously massive objects and the universe's large-scale structure may be well characterized. There are various potential theories of quantum gravity being developed, but general relativity has not yet been united with the other fundamental descriptions.